The lab final is this, so I have it. It's all ready.
So we have both our third test and the lab final this Thursday.
Yeah.
Okay. And like, what should we study for the lab final? Just the questions at the end of the lab reports, or?
That will help a lot, actually. Yeah.
Okay.
I will even say that that's a bit like that will prepare you, that will over prepare you, but because the questions, the lab final is a lot of multiple choice based on concepts that you did in the lab, like electric field lines, resistivity equation, current, circuits, but theoretical questions that you don't have to solve anything, that you probably have to just write down something about it.
So you're not going to have us like perform anything. It's just going to be like a written exam.
Yeah, I think there's 1 or 2 questions. It's 14 questions, 1 or 2 questions only where you have to do a couple of calculations here and there. But it's mostly conceptual.
Okay.
Yeah. So trust me, it's more like a lab exercise rather than an exam. And you can finish it in like 20 minutes, 25 minutes. So that means that you have enough time to review for the exam free. Now, exam free, I'm doing a review. By the way, on Wednesday, class is going to start at 12. I can't be here later than 1-ish. So I'm going to start class at 12 and I will record it. It's just review. Just review 12 to 1 or 1:15. I will just go over similar questions or questions that might be on exam free. So if you miss class on Wednesday, it's going to be recorded. So there's nothing new on Wednesday. So I'm doing it like that. Even tomorrow, I think I can start a review, I think, for the exam. Because today, you will see that it's quite fast where I have to go over corrective optics, which is assignment 15. And then at the end of today, I will start introducing interference. So this, wave optics, I will do Young double slit experiment, and maybe even diffraction. And then tomorrow we can do problems. I start with a review. So I will say the best thing you can do, is start catching up with even if you don't finish the homework, right? Try to do at least 2 problems here, 2 problems here, like, and then after the exam, you can go back, because I'm going to reopen all the assignments, by the way. Between tomorrow and Wednesday, I'm going to reopen everything. I did say there's going to be penalties, so I know who hasn't submitted yet. But everybody can go and redo homeworks, re-practice questions. You can start doing that starting this week to prepare for the final. All right. So I think that would be fair. For the last final, you can bring, I said no, but you can bring your own formula sheet, but you probably won't need any formulas on the lab final. You won't need anything. It's all based on what you did in if you understood what you did on the labs, trust me, you're going to finish the exam like very quickly. Okay. Any other questions? So again, try to start doing assignment 12 to 15 today. 2 questions for each assignment, or 3 questions, and that should get you ready. Honestly, that should be more than enough. And then you can go back and refinish all the assignments, right? Just be smart which questions you want to attempt. Like focus on when you have a negative image and negative magnification. How do you do ray tracing or refraction, reflection? Think about what you did on the lab.
Wait, Professor. So if a question have a negative magnification, does that mean it's behind you?
No, magnification is only related to the whether an image is inverted or upright.
So if it's negative, it means it's inverted.
Yeah,
Okay.
Be careful with that. I will normally suggest using behind or in front of the mirror with the virtual or real images for mirrors. Yeah, for a mirror, a virtual image means is behind the mirror.
have to do any like ray tracing?
There's, yeah, one question. And it will help if you do in another question. You don't have to, like I'm giving you the graphs, in fact, in most of the questions. But if you can trace rays, that's what I'm saying. Practice the questions that you have to like refract or go through mirrors and lenses. You probably won't need it, to be honest. Like if you understand, like he has asked, right? What's virtual, what's behind the mirror, it should be fine. But it helps. It does help. Yeah, it helps if you know that. And then a question about today. So today, let me just go over this. So we're gonna go over this, what we did, nearsighted and farsighted, all right? So these were the slides that we covered last week, far point, near point. So let me show you how we use that, because we didn't do problems on that. Am I sharing the screen? Yeah. So the first question, it says that the near point of a person is 70 centimeters. You know already from the lecture that that's too much. So if a person is trying to read something, because of the near point, the person won't be able to read a book properly. Something about the terminology in this chapter, right? If they tell you, if they mention that the person has a near point, that means that the person is farsighted. So that's something that you want to make sure is clear. If they tell you that a person has a near point, that means that the person is farsighted. And if the person is farsighted, you are gonna correct. You're gonna correct his eye vision using a convex lens. So you need a convex lens. All right. So the near point is 70. What should be the focal length of a lens to observe an object 26 centimeters away? So the object is too close. Even if you decide to do the graph, and that's what I'm saying. Do you have to do the graph? No, but it's just as an exercise, show you how will this look. So you have the person's eye here. So let's put here the eye. And the near point is here. So you label it like N. That's 70. Now, the person is trying to see something that is here. That's the object distance, 26. So how do you find the focal length for the lens to correct for this? Well, you need to use a convex lens. So the object creates, so the lens creates an image of this object here. Right? We did that during the class on Thursday. So here is where the image is going to be. That's the image. So because the image, you want to write this, the image will be virtual 70 centimeters from the eye. So that's how you find the focal length. This is your Q, this is your P. Now we have to label that, we have to be careful with the signs. P is this, Q is, because it's virtual, negative 70. Okay, so now you can solve the problem. To find the focal length, you use the lenses equation. 1/26 minus 1/70 equals to 1 over f. Now, if you solve these fractions, focal length is 26 times 70 divided by 70 minus 26, that's 44. Right? So here is what your whole signs, right? You have to be careful with that. You see, Q was negative there. They don't tell you, but you have to realize based on the information given. So you get 41.4. 41.4. So that's the focal length of the lens. No, positive, because it's a convex lens. So that's what you need to study. I feel like the math is the easy part, it's the concepts. So if it's a convex lens, you have a positive focal length. That makes sense.
Wait, so professor, so N will be the point where, so the object is 26 centimeters in front of you, right? And the person near sight, so they can see something 70 centimeters away from them at maximum.
They can see objects that are 70 centimeters from the eye or beyond, because the person is farsighted.
So what does farsight mean? They cannot see too far away.
They can see far away.
They can see far away, but they cannot see close.
They cannot see close, yeah.
So what we're trying to do is move the image back to 70 centimeters away, right? Which is why it's minus, right?
Yeah,
Okay.
yeah. That's a classic problem on this chapter, by the way. That's a problem. That's a problem that you see on sandwich. So that's, again, you don't have to do this, but it kind of shows you what's going on. And then what's the power of that lens? So the power of the lens will be 1 over f, right? So here, the power of the lens, the power will be 1 over f, but 1 over f has to be in meters. So 1 over 0.414. All right. So to
Wait,
find the power of the
Professor.
lens, you have to change the focal point in meters, and I get 2.42.
Wait, professor. Well, so wouldn't the power also be the magnitude?
No, it's different. That's a different concept. Remember that the power of the lens has to do with refractive power. It tells you the refractive power of the lens.
So what's the difference for magnitude and 1 over f?
Magnitude is the length of the focal length, for example. The power of the length is the inverse of that. 1 over f is the power.
Okay.
Okay? So it's not like the power that you guys know from mechanics. It's a different it's a different term. It's the term that they probably use in ophthalmology to prescribe lenses. The power, the refractive power of the lens. All right, so there you are. Okay. All right. I want to leave that in there, and then there's another example on the right. So on the right, it shows you a person can see clearly with a negative free diopter lens. What is the power of the lens? What condition does the person suffer? What would be the new focal length if it was switched to contact lenses? Okay, so To find the power of the lens, we do this equation, 1 over f. So here, the power of the lens, the power will be 1 over f, which is, it can be negative, by the way. Wait, what's the power or what's the focal length? What's the focal length? The power is in the, what is the focal length? What is the focal length? If you use the power, you can find the focal length. To find the focal will be negative, because it's negative, 1 over 3, but because the odd term is 1 over meters, you want to find the focal length in centimeters, so you multiply this by 100. And you get negative 33.3 centimeters. That's the focal length. So because it's negative, that lens is concave or biconcave. It's a concave lens. All right. So if it's a concave lens, what condition does the person suffer? We use concave lenses to correct nearsightedness. Yes. Farsightedness is for convex lenses. Concave lenses goes for nearsightedness. So this person has nearsightedness. What does that mean? That the person can see objects that are close to the eye, near the eye. Objects that are far, the person cannot see. All right. What will be the new focal length if you was switched to contact lenses? Okay, we need to know what's the distance between the lenses and the eye. So let's see. We are right out here. Okay, so yeah, so the person has the lenses 1.5 centimeters from the eye. So the person can see clearly with these lenses when they are 1.5 centimeters from the eye. So what will be the new focal length if it was switched to contact lenses? So in this graph here, if you think about it, right? If you were to do a graph, those lenses, that's the eye here. They place the concave lens. The concave lens was placed 1.5 centimeters from the eye. So if you switch to contact lenses, you are gonna push the lens to be here, right here. So you have to add 1.5 to 33.3. All right. So the new focal length, you want to write here, focal length new will be negative 33.3 minus 1.5. That will give you negative 34.8 centimeters. You are pushing the lens to be where the eye is located. So there you are. Okay. So two examples. One, we use the length equation. One, we use the power equation and our theory, right? The concepts, nearsightedness and farsightedness. There you are, both. All right. Any questions? All right, let's do prescription of lenses now.
Wait, Professor, for the second question, you only have 1 over P because you're not seeing something far away. No, far away, right?
For part A?
Yeah, you say F equal -1/3.
Yeah, that's 1 over P, and then you multiply by 100 to change to centimeters.
Yeah, we don't have a Q because we're not looking through anything, right?
Well, they are not asking you anything related to objects. It's a general question.
Okay, got it.
But this one does give you P's and Q's again. So let's do this. So it tells you that the near point of a person. So the near point of a person is 50 centimeters. All right. What focal length should a lens have to enable the person to see an object 25 centimeters away? So part A will be, what should be the focal length of a corrective lens? Or what should be the focal length of a lens to observe an object 25 centimeters away. That's part A. So again, they give you a near point. If the person has a near point, that means the person is far-sighted. If the person is far-sighted, the type of lens that they're going to use is a biconvex or convex lens. That's the type of lens that a person is going to be prescribed. The person wants to observe an object 25 centimeters from the eye. So that will be your object distance. So this will be your P. P is 25. What about the image distance? If you remember from the previous graph that we did, you want the image of this object to be at this point, the very least, at the very least. So Q is -50 centimeters because you are going to obtain a virtual image behind the object, right? So to find the focal length, you do 1 over 25 minus 1 over 50. equals to 1 over f. 2 over 50 minus 1 over 50 equals to 1 over f. F equals to 50 centimeters. All right? That will be the focal length of the corrective lens. That's part A. We just did that, so that's easy. What will be the power of this lens? So, what will be the power of that lens? What you do is you change the focal length to meters, right? To find what's the power of a lens. You will just do 1 over f, but f has to be in meters, so 1 over 0.5, 0.50, that will give you 2.0 diopter. You can even later. So that should be clear now. Part C, however, changes the idea a little bit. In part C, it says that we're going to repeat the problem, A and B. If now we assume that the lenses are 2 centimeters from the eye. So all of this is if you assume that the lenses are contact lenses. There's no distance between the lens and the eye. If we want to make it more realistic, what if the eye is here? The near point is here, of course. The object is here, and the lens is going to be placed here, 2 centimeters from, this is 2 centimeters from the eye. So this is the lens, and I'm gonna call this a what if, or repeat. A and B, if that's the situation now. So what do you think will change if the lens is now 2 centimeters from the eye? Before, we assumed that the lens was where the eye is located. The focal length will change, but by how much? That's what you have to find.
Subtracted, would that increase by 2?
Huh?
Would it increase by 2?
No, it's not as simple as that. Be careful, because the way you obtain the focal length is by doing the 1 over p plus 1 over q. The focal length will change. The focal length changes because the object distance and the image distance, they both change. So the object distance was 25 before, but this was 50. This was 25. But now it's not a scale, by the way. If this is a 2 and all of this is 25, how much is this? Yeah, so 23 is your new object distance. And what will be your, this is where the image will be. Image. So what will be the new image distance? What's this? 48. So this is your new object distance. This is your new Q. Use those like we did here. And I'm gonna do it here so you can see the difference now. So let's do this division. And let's do 1/23 minus, this is still virtual, 1/48 equals to 1/f. F equals to 23 times 48 divided by 25. Is that clear, everybody? $44.2. Yeah, I got 50 before, right? Now I get 44.2 centimeters. It changes, it's reduced, but look by how much. That's a new focal length. And then part B was the power. So the power of the lens will be 1/0.442. Huh? 2.3, so the power increases by 0.3. So 2.3 diopters. Another, that's a classic one. So I gave you 3 examples today. One of those for sure will be on exam 3. All right. And as you can see, guys, it's very easy. The math is very easy. It's the concept. So make sure you review your near and far sightedness. And I will say, as I said, that's why I give you a suggestion. You may want to go after class today and check a couple of problems from assignment 15, a couple from assignment 14, and that will give you everything you need for lenses.
Wait, so professor, so this person is far sight, so they cannot see far away, right?
They can't see far away. They cannot see
close. So with this is why so this guy could see a maximum 25 centimeter in front of him.
50.
Okay.
So
we
50 is where is the maximum he can see.
Okay.
Below, no.
Okay.
So that's something that you guys need to really.
Around 50 is the minimum.
Huh?
Minimum distance.
Yeah, minimum distance.
Rather than maximum.
Remember that for test 3, you may be able to write not a whole bunch of paragraphs. Maybe you want to write nearsighted goes to concave, farsighted goes to convex lenses. But in the final exam, you won't have that. The formula sheet for the final is just formulas. So just keep in mind that. All right, that's why I sent an announcement. Make sure you do good in exam 3, because with that you can basically just pass. You'll be good to go. But yes, so this is just what we did on lenses, but apply to corrective optics. All right. Okay, so let's do the magnification now, because we also talk about magnifying glasses. So how do we use magnifying glasses in real life? Remember, glasses or lenses, which are glasses, they magnify objects like we've seen, but the way we've seen magnification is just the lateral magnification, right? We don't look at every dimension of the object. Angular magnification does attempt to do that by looking at the angular magnification of the object or the image in this case. So a good example will be by using a magnifying glass and an object that we're gonna conveniently draw it symmetrical to the axis. So so this example gives you a leaf. So we have here the axis. All right. And it shows you a leaf here. And it's symmetrical. So like that. Okay. And that leaf is in front of a lens, all right, which is 75 centimeters from this lens. So let's not make it scale to be like that. So it's 75 centimeters from this lens. The focal length of this lens is of 45. All right. And there's going to be a person here looking at, so this is the eye, looking at that leaf through the lens, and that person is located at 1.46 meters away. Yeah, so we want to see the angular magnification based on based on this person. All right, but there are two questions. The first question is, what's the magnitude of the lateral magnification? And B, what is the angular magnification? So those are the questions here. A, find the lateral magnification, and B, find the angular magnification. Find the angular. Okay? All right. Look, as I said, if you have just one lens, the focal length, and the object distance, to find the lateral magnification right here, to find part A, lateral magnification is just negative Q divided by P. So that's P. So I need to find Q. How do I find Q? With a 45. All right, so let's do it here. 1/75 plus 1/Q equals to 1/45. Q will be, let's do it here. So Q will be 75 times 45 divided by the subtraction, which is 30. Right? 75 times 45 divided by 30. 112. I get 112.5 centimeters. All right. So this is my cube. So in here, minus 112.5 divided by 75. So that will give us 1.5. Nice. Negative 1.5. That's the answer. So that's the answer for part A. For part A, guys, you should be able to do it with what we did before. Just the length equation. How do we find the angular magnification? For this, I will suggest you guys do this. So what I'm doing right now is I'm just doing the ray tracing of this. This is my image, right? That's the image that we found to be that 1.5 more than that. So Q was this. So all of this is 112.5 centimeters. Now, the distance between the magnifying glass and the eye is 1.46 meters, but this in centimeters is equal to 146 centimeters. So that's okay. What is the angular magnification? We look at the angles between the eye and the image. So that's why I did a ray tracing. You want to look at this angle. This is theta prime. That's the angle respect of your eye to the image. What about the object? Well, that's why I said that the leaf was symmetrical to the optical axis. Because I can look at the angle between this, I took this H, so I did, and then to get this image, I use this. Now I'm gonna use this, which is the same height, is symmetric with the eye. So you need to trace, you need to draw a line all the way from like this. So let's see if I can. Like that. You want to do this triangle. There. So this will be your angle theta. The angular magnification, so let's write here, angular magnification is equal to theta prime over theta. 99% of the time, theta prime and theta are very small. That's going to be important. Why? Because I have two right triangles here. I have this one, and I have this last one there, right? Let's find theta prime. Theta prime, opposite is the height of the image. The adjacent is 146 minus 112, right? It's all this. This is the subtraction of 146 minus 112.5, which is this as well. So 146 minus 112.5 is 26 plus 7 is 33.5. Right? Yes. So that is my triangle. So you can write like this. tangent of theta prime is height of the image over 33.5. Do you agree or not? Opposite over adjacent. So you get. All right. Now, what about theta? Well, let's look at this triangle. This one here. We have that the tangent of theta is like that. The tangent of theta is height of the object divided by all this. And what's all this? 75 plus 146. Yep. So the tangent of theta is the height of the object over 146 plus 75, that will be 216 plus 5, 221. 221, right? That's the tangents. Now, theta prime and theta are very small. If the angles are very small, you should know from math that theta prime is basically tangent of theta. So theta prime is hi over 33.5. And theta is height of the object over 221. Well, there you are. Now I can do the angular magnification. I divide these equations. If I divide the equations, look what I get. I get height of the image over 33.5 divided by height of the object over 221. Now, if you do your fractions here, you get the following. 221 over 33.5 multiplied by height of the image over height of the object. And what's height of the image over height of the object? What's hi over ho? Is this. Yeah, 1.5. So theta prime over theta is 221 over 33.5 multiplied by negative 1.5. That will give you the overall magnification. Let's see what we get. 221 over 33.5 times 1.5. I get negative 9.9, or actually negative 9.9. That's the angular magnification. So a magnifying glass magnifies an object 10 times more than magnifies an object by 10, which is actually, there you are. That's an application of magnifying glasses. We talked about that last class as well. All right, so the first part was just what we did before. The second part is a bit of trigonometry and triangles, right? The triangle with the image and the triangle with the object. All right. Practice a problem from assignment 15. There's a problem like this. That's why I did it. All right. So it's recorded, but I want to make sure that you guys understand, right, where we get these relationships, right? Theta prime is the height of the image over this side, which is 33.5. You get that from the geometry of the problem. And tangent of theta is the angle between the eye and the object here. And that's basically the height of the object over all this side, which is 221.
say like the distances, for example, go lens to the eye,
Was closer.
it's closer.
The magnification probably will be smaller than that.
Smaller, and then
Yeah.
that means then that we couldn't use the assumption that theta
You can always, normally you can,
normally.
no, you can, because we're looking at objects that are small, right? Since objects are like the size of a pen, and you're looking at 1.5 meters is the distance between, is basically a bit less than my height, and you're looking at objects that are small. So you can assume that the assumption of tan of theta equals to theta is when the angle is less than 10 degrees. So it gives you a good range. All right. Now, if the angle is beyond 10 and you do the assumption, it's still not that bad. It's the same as when you guys did a simple pendulum and you get that the period is 2 pi square root of L over G. That only works if the angles are smaller than 10. If the angles go beyond, well, I would say beyond 15, you have to start adding a series of, like the differential equation gives you a more complex solution that depends on the angle. All right. But this approximation it's okay. I look at this number, for example, and even this. If the height of the image is 2 centimeters, 3 centimeters, okay, all this. Still, and even this. That's why you can assume that. But yeah, the problem will make sure that they will give you numbers that you are comfortable assuming that. Okay. By the way, guys, normally for angular magnifications, since lateral magnification, there is this inverted and upright. For angular, there is not such a thing. So you can just leave it like that. Positive. Okay, you can leave it as positive. It's just telling you how much is being enlarged. All right, guys, guess what? We are done with geometric optics. All right. Are there any questions? Anyway, like before I move on to web optics, which I will finish tomorrow, does anybody have any questions about anything that you have come across on the assignments? Something that might not be clear? Okay, so I will go, there is a animation I'm gonna show on the computer, right? So let's go into web optics, which is that last section before modern physics. This section also will help you solve the last assignment, which is extra credit. So assignment 16, and I might publish the other extra credit assignment, but if you complete assignment 16, you will get an extra 5%, all right? Some of you probably don't need it, but still use it to study the material, all right? And I will say that the final exam, 90% of the final exam will be up until what we do today and tomorrow, which is diffraction interference. Next Monday and Tuesday, I will do modern physics, and that's it. All right. Next Wednesday, I might be here in the college to answer questions. So please, I will say, guys, be responsible. If you think that you need to do good in the final, you want to be here next Wednesday to do some review. I won't do a class, but I'll be here in the classroom to answer questions. Let me show you where you can find a practice final now. Okay, if you guys go to, what is this? If you guys go to files in the Canvas site, where you found the equation sheets, you can find this final exam sample. Now, keep in mind that this final exam was a final from a few years ago when we used to have 60 questions. In the final that you guys are gonna have is only 30. So, for example, in this exam, there may be 2 or 3 questions of one topic, Coulomb's law. In the final exam that you guys are gonna have, I'm gonna have just 1 question about Coulomb, for example, right? This should give you an idea of what you may expect. What type of questions, the length, how long it takes. Like, look at that question on circuits. Very easy. Look at that question on capacitors. Very easy. Or this one we had in a quiz, I believe, on an assignment, right? Look at this question about power. They give you the power, they give you the voltage, find the current. So some of those are just applying formulas, right? Look at this question. I did this question in class, right? So this question wasn't the assignment, I believe, something like that. So make sure, remember induction there with a magnet. So make sure, or this, right? I told you guys that question there. So make questions about mirrors, lenses here, refraction. So this will give you a good idea of what's gonna be. And in fact, probably on next week, I might do some questions from the previous final, the final that I gave last semester. It's not this one, by the way. This is the one from the college that they give us, so you guys can have. Please, by the way, you see what it says here, right? So you shouldn't be uploading this anywhere. All right, be careful. Like when you see this, don't be uploading it in those websites, because if they track it, it's not gonna be nice for you guys. And you're gonna be harming students from other semesters that they might need this document, right? And they might take it away because of that. So make sure you don't publish that. So that's that. And what we're gonna do today is in here. Chapter 24. So the exam free is up until chapter 23, right? So chapter 24, 25, 26 will be all in the final. All right. So interference and diffraction, the slides are awesome. The slides are here. But I want to show you an animation of this so you can see what this is about. Everything that we've done in optics so far, right? You see right now on the board. That's all based on ray optics. And I explained this last week when I said that we were going to simplify the notion of light from an electromagnetic wave to rays. The whole idea now is to go back to the study of light as a wave. And on Monday, we're going to do the study of light as a particle. And then you guys will understand what we know as a dual behavior of light. So look at the following animation there. How many of you have seen this in the past? And do you guys know what that is? You have a light source. By the way, normally this is a monochromatic light, like laser pointers. And you turn it on and you see waves. And what are you seeing there? You guys haven't talked about that in chemistry? Yeah, when you guys talk about photons. Yeah, the photoelectric effect is more the light as a particle. But yeah, man, so you guys have studied light. Yeah, so what you guys are seeing there is the main evidence that was used to show that light has a wave-like behavior. You can replicate this experiment with sound and water waves. That's water there. And with water, you expect water waves to behave like that. So you have the amplitude of the waves, or even with sound, you can make this closer, and you can make the aperture not too big, and then you have sound, and then it diffracts. When you have only one slit, that's when we start talking about diffraction. That happens with water, that happens with sound, because they are waves. That also happens with light. Now, we don't see light. Yes, I'm not talking about the fluorescence. That's reflection of light, right? Light incoming to us, or light coming from the sun, we don't really see it, right? What we see is reflection of colors or emissions of wavelength, but we don't really technically see electromagnetic waves. But we know they have a wave-like behavior. First of all, from Maxwell equations, I did show you that before we did optics or ray optics, but also because of these experiments. Now, the major one was that two-slit, because what was believed is that if there are two slits, light will only go through the two slits. So if you remember what I showed you before with light, yeah, you see the screen? You have 1, 2, 3, 4, 5 bright fringes. You see these blue rectangles there? Those are bright spots that you can see on the screen. We call that the interference pattern. But you also see the dark spots. When we do diffraction, we're going to be caring more about the dark spots. In the double slit experiment, we care about both, because the bright spots, the bright fringes, they are an evidence of constructive interference. How many of you have done waves here, mechanical waves? Do you guys do mechanical waves or harmonic motion? But you didn't do waves.
It's sound waves, so like Doppler effect, or the string tied on one end.
Okay, so you did that.
Yeah.
So then you did the nodes.
Yeah.
Yeah. So if two waves are incoming to one another, right? There are two possibilities. Either they cancel or they add up and they create a larger wave. That's what I mean about constructive and destructive interference. You experiment that with your radio. When you guys are driving around certain areas, you will see that the radio signals are very bad. That's because of interference. That's destructive interference. If the radio signal is good, then that's good, right? But you may have constructive interference in some cases, right? In mechanical waves, yes, you see the node adding with another node, like the bumps, and you create a larger wave. With this animation, you can sort of see that when the waves are interfering with one another, the one from the bottom and the one from the top, there are dark spots that are being formed. That's because of destructive interference. And the bright spots are due to constructive interference. When they arrive to the screen, you start seeing the pattern there. Now, for light, that was a huge discovery, because the idea of light behavior as a wave was not very clear. Once this was proved and shown, that was all good to go. The second sort of revolution was when we discovered that light also behaves as a particle, but that will come later. So that's what we're going to be talking about in this chapter. Now, there's this whole idea of diffraction as well. I don't know how many of you have seen this before. Diffracting patterns in nature. Newton rings. There's also Einstein rings due to gravitational field. As you know, gravity affects light. By the general relativity, we know that gravity affects space and time, and light travels through space. Therefore, light will be affected by gravity. But A diffracting pattern normally occurs when monochromatic light goes through a peak hole or a small aperture. And you see these wings form. They actually can't, you see this is the aperture, and this is what happens when you illuminate the aperture, right? You can see this pattern here. There are some experiments that we can do with this as well, all right? But pretty much these two experiments, especially that two-slit experiment, they show you that light behaves as a wave. That's another application of diffraction there, right? So what are the sections for this chapter? The superposition and interference, the Young two-slit experiment that I just showed you. We're not gonna do this. I may talk a little bit about this tomorrow, but not much of this. But we're gonna be focused on diffraction, resolution, and diffracting gratings. Especially this is very important, all right? Because diffracting gratings is what we use in lab to break light into components. So if you have ever seen or used an spectrometer, spectrometer is a device that we use in telescopes, by the way. We make light pass through an spectrometer that has a prism. And as you know, light refracts on the prism, but diffracting grating also is used so you can bring light into the rainbow colors, all right? So we can perform experiments and analysis of the spectra of light. So this is the idea behind interference and superposition. When you have destructive interference, that's the equation that you guys are going to use. But how do we get that equation? The equation for interference and diffraction is basically the same. The only difference is what you are seeing there, that we have a condition for dark fringes and there is going to be a condition for bright fringes. So I'm going to leave that in there and I'm going to draw you on the board the Young double or two-slit experiment, all right? Okay, so the experiment is basically having two slits with a separation that shouldn't be very large. And you have light incoming, like you saw in the animation. Sometimes they also show you the light incoming like this with a wavelength lambda. Remember, light has a wavelength. Now, there, right? When light goes through these slits, as you saw in the animation, we have a screen. Normally it has to be a white screen. It can be any that allows you to observe the pattern. So I'll do this right now. There. That's your screen. So basically, you have, just like we had in the before, we have like a axis here, right in the middle, and then you have basically the central point. You are gonna see a bright spot here. Now, you're gonna start seeing bright spots here, 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 right? But also here, 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 here. Those are your bright fringes. Now, let's suppose we want to look at the one from there. So light is going to enter here, and there's going to be a constructive interference that will lead to there, like that. So light is going to travel from these two slits all the way there, or below the center, above or below. But you can clearly see that the path here is L1 and here is L2. There is a difference, right? This is more than this. So the condition for interference, there are conditions for interference. You have constructive or destructive. For constructive, basically we look at this. We look at the difference between L2 and L1. Now, the distance between the slits is normally labeled with lowercase d. So we look at this angle theta. L2 minus L1 is this. That's where your d sine theta comes from. If it's constructive, the difference, which is that, is an integer multiple of lambda, m lambda. This is your first equation for constructive interference. So this is for bright fringes, for bright spots. All right. And normally m goes from 1 to and above. So m can be plus or minus 1, plus or minus 2, plus or minus 3, dot, dot, dot. Minus is below the central. Plus is above the center. All right. So m is basically the order. So this is first order, second, third, fourth. All right. That's how we do this. Now in real life, we normally see the first order or this one here, of course. The second one, it may be a bit tricky, but we can see it. Above the second one, depending on the wavelength of light, is difficult. All right. It becomes very dim to observe. But there you are, that's your condition. Now in the slides, you also have this equation. The conditions for destructive, because you can have also dark spots. Dark spots will be here. I'm just using this blue color. Right? Those are dark fringes. So the conditions for destructive interference. That means dark fringes. You have two equations, right? sine theta is n minus 1/2 lambda. This is when you are above the central maximum. And then you have d sine theta equals to m plus 1/2 of lambda. That's below the center. Well, m is always an integer. So for this one, if m is 1 or 2 or 3, what's 1 minus 1/2? A half, which if you think about it is this. 1/2, 1, 1.5. Well, 2 minus 1/2, yes, this will be 1.5 or 1.5. All right. So we're normally going to be focusing above the central. So this is the equation that we're going to be using for dark fringes, and this one is the one for bright fringes. All right. That's the idea behind the Young double slit experiment. All right. What else can we obtain from this graph, though? In many experiments, when we do this in a lab, we want to know how far is the bright spot or the dark fringe from the center. We call that the vertical distance. So we want to know these vertical distances. All right, so let's see. I need to just erase these lines for now. We don't need this anymore. There you are. So, see this? That's all the same. But now I'm going to look at, let's suppose the vertical distance between the second bright fringe and the center. So I'm going to be looking at this y. I'm going to call it y2. So I can do this. By geometry, you can prove that the angle theta is the angle between the middle here and that. So this is now your theta, or in this case, I'm going to call it, let's call it theta for now. That theta there is theta here. All right. So that equation works. For the second spot, I will say that d sine theta equals to m is 2 lambda. That's correct. If I know d, and if I know the wavelength, I can find the angle theta, which are normally very small. Okay. How do I find y though? To find y, I need to know the distance between the, I need to find the distance between the slits and the screen. I need this distance. So I'm going to call it capital D. And I have here a right triangle, right? So y2 will be D tangent of theta. That's the equation for the vertical distance. If I want this, I can call it theta 2 here, tangent theta 2, sine theta 2. If I want the one for the bright, for the first one, it will be d tangent theta 1, and so on. So that's another equation that we use in this sort of situation or experiment. All right. So that's the idea. All right, and that is basically what you have to use for the problems on assignment 16. Of course, don't worry because we're going to do some examples, but that's pretty much the theory and the conditions behind constructive and destructive interference. All right. Let me show you what else we have here. So in the slides, they show you this superposition, and they show the illustration of what I just showed you with radio antennas. Just remember, electromagnetic waves, they also are radio wavelengths, right? So we have the conditions for constructive and destructive in there, right? That is what you guys also did in mechanical waves. So it's the same, the path difference between L1 and L2 is what determines when you have constructive or destructive interference. Now, for monochromatic light, this is what happens, right? When light goes through two slits, you see the interference pattern like we did, like you saw in the animation. I closed it already, but maybe I can have it here. Yeah, so I can just put the slits. Oh, there it is. Like we had before, right? So that is basically what you see on the board, or what you saw in the board, and what you're seeing in the slide here. All right. Remember that we can use all these ideas of wave and direction and how it propagates by using the wavefronts. You're seeing there, like we talk in the ray optics, right? But now, instead of just talking about rays, we talk about the source as wavelets, right? And it is shown in the picture in there. And this is what we know as the Huygens principle. It's named after him because this is the scientist that actually performed several experiments with light before Galileo, before Newton. So there you are. That's the equation that I showed you before for constructive interference. Keep in mind that for M0, you get a trivial solution, right? If M is 0, what will be the angle theta? 0. So you're looking at the center. There is no angular displacement, right? That's the demonstration I showed you already for destructive and constructive. Yeah.
Does changing distance between like each slit,
Yeah, it changes.
increasing or decreasing, does that affect the amount of light spots?
Yeah.
And then
It will affect the angle because d sine theta, they are inversely proportional. And if it affects the angle, it affects the visibility. Theoretically, you can see as a certain amount of slits or fringes. The problem is that depending on the illumination of the room, depending on the equipment that you have, you may not be able to see more than 2 on each side. Yeah, depending on the wavelength of light as well. Because wavelength is also a factor.
So then what happens if you like add even more slits rather than 2? Say if you add 3, 4, but keep each distance is the same as if you do 2, would that also affect?
That's when you start getting more into combination. Like you could see the pattern will be different and you wouldn't have this relationship. This is only works for 2, right? Because for 2, we had L2 minus L1. If you have more, then you have different path lengths. How many slits you want to have? Like 1 here, 1 here, 1 here, so that you have another line going like that. So you still have interference, still waves, but you cannot use these equations.
Okay.
So the study will be different. I mean, how it will be affected, it also depends on the size of the aperture. So in the animation, they give you the, for example, here, you can vary the width of the slit. And that's something, oh, there's a question here. Okay, let me just finish with this and then I'll answer because we're about to finish anyway because I want to do problems. I'll do one problem today and then tomorrow, please guys, make sure you are in class because I want to do all the problems on diffraction, interference, and gratings, okay? And if we have time, we can probably even review for the quiz. So be responsible, all right? So in this experiment, in the equation that you see on the board that you see on the slides, there's nothing for the width of the slit. The slit separation is lowercase d. So in here, this d is the slit separation. It's not the width. The width will matter when we do diffraction. Because in diffraction, that's when we go into just one slit and you care about the width. So that's also a factor that we don't really pay. But the thing is that we assume the width of the slits to be very tiny. So I remember doing this experiment a few years ago when I was teaching in another school, and the student did diffracting and interference, double slit experiment. And we used lasers and aluminum foil, and we cut, you know, those paper cutters that you guys, so we cut very thin slits. You want to make them as thin as possible.
If you make it big though,
Then you probably won't see the pattern. It's affected by the width as well. I tried to do it before we started class. I was trying to play with this a little bit, but look at the units of it's in nanometers. They're very small. They're very small. Yeah. So tomorrow the quiz is gonna be published in Canvas. All right. So I was thinking about giving you guys some paper, but then I remember that Wednesday we have the class online. So the quiz will be open as soon as we finish class, and then you need to show work though. So you need to, it's basically what you guys did when you were in the remote years, right? You will take the exam and then you will upload it in Canvas. I'm still not sure with the due date because I do want to restrict it for tomorrow. So if it starts at 2:50 or 3, I wanted to make it due at 6 or 7.
Wait, Professor. So the quiz is on chat, what, Cgage?
No, it won't be on Cengage. That's the thing. You will find the quiz in assignments. It will be uploaded. So let me open this now before I forget. So I have to change this, you see? So it's not gonna be WebAssign because I feel like WebAssign quizzes sometimes. No, I want to change the type of questions you guys have for this. So kind of like practice for the exam. So, yeah. So quiz 4 will be on Canvas. You will upload a file, so no website. And
Will it be on paper?
yes, so you will print the paper, you will work on it, and you will upload it.
all work.
Okay.
Now, if you feel comfortable working on a computer with a tablet, but you have to show work. The
Okay.
questions require you guys to show work. All right. So the thing is that the due date tomorrow. So tentatively should be tomorrow at 7. That's what I'm thinking. So you guys will have 4 hours after class to submit it. But I don't know. I have to see what the other students say. Okay. But that's, so I haven't uploaded it yet, but I have it ready. The quiz is ready.
Okay, so it's due today at 7 p.m.
Tomorrow, August 8th.
Yes, I. Today's all the same.
To the 7th. To the 7th. All right. That means on Wednesday you will have your grade for sure. And that's when we do the review for Thursday. Remember, when I'm also doing, because on Wednesday I can only be here till like 1 something. So I can't, you know, I'll be here early on Wednesday though. On Wednesday I'll be here around 11. So if somebody wants to come and ask questions, you can come.
Wait, so Professor, tomorrow after lab, class will start at 1 and will end at 3, right?
And tomorrow is normal day. Tomorrow
Okay,
is
but
normal.
Wednesday is gonna be different.
Wednesday, I want to change it at 12 because of family thing I have.
Okay.
But it will be recorded like today. So, and it's not new topics, it's a review. And we might start doing a review tomorrow. So, should be fine. Okay, so to finish with this, guys, this is the experiment, the summary. It's kind of what I show you here on the board. All right. But now you have it on the slides. I will say that the main thing is the equations. With the equations, you should be able to, and you will see when we do the problems tomorrow. All right. One thing, guys, I didn't mention this before, but it's in this chapter anyway. How does the wavelength changes when you go from 1 million to another? When you go from 1 million to another in refraction, I mentioned that the speed of light changes. But remember, speed of light is lambda times frequency. So if the speed of light changes, you will expect either of those, frequency or wavelengths, to change. We know that frequency doesn't change when light is refracted in the atmosphere. So what changes? The wavelength. So the wavelength is changed by the factor of n. So the wavelength in a medium n is equal to the wavelength in vacuum divided by n. All right. Don't worry about this equation here, just this one here. All right. The wavelength change when you go from 1 medium to another. And then let's talk a bit about diffraction. All right. And to talk about diffraction, we can also even use this again. What is it? Okay. We just have to use one slit. So this is the idea of diffraction. All right. Depending on the wavelength of light, now you can already see that in the screen, there is a pattern that is going to be formed. Even though there's only just one slit, just like sound, when you talk or when there is music in one room, you can see it, you can listen to it across the hall. When somebody is talking, the same with light. If you turn on the light of a room, light will be diffracted and it will illuminate parts of the hall or sections around it. That's because light diffracts. And we can study diffraction like we did interference. Even though we have one slit, we can do the study of interference and we get the dark spots. We get the diffraction pattern as you see on the slide. So why do we get that? Because just like with interference, we can see a difference on length between the top side, like if we magnify the slit, between the top side of the slit and the middle part of the slit. So we divide the slit into two. That's your angle theta there. And then just like we did before, this is W half now. This will be W half sine of theta. So if we take the whole slit, it will be W sine of theta equals to lambda. But that will be for the first order, the first dark fringe. If you go to the second, the third, and the fourth, that's when you start having 2 lambda, 3 lambda, 4 lambda. So the equation for diffraction is the same as the equation for interference. But instead of D, now we use W. So D in interference was the separation of the slits. Now W is the width of the slit. It's a single slit. And M is the order. And just like before, it can be plus minus 1, plus minus 2, etc., etc. All right. So what we need to add on diffraction is resolution. So you remember here, when I show you the diffraction one, you see that there are different bright spots, right? And look at if I have this, or even, there's no, two I want to show you. There it is. Perfect. Angular resolution. So we can study diffraction using a source of light, and this is what we get there. However, when we look at the universe, right? When we look at different solar systems out there, different stars, normally we see that they come in pairs. Like, for example, Sirius A, Sirius B, like binary systems. And the problem with looking at a binary system is this. If two stars are too close to each other, and if the telescope has a poor angular resolution, you observe the picture at the bottom. However, if you increase the resolution of the telescope, you start seeing the two objects as what they are, two separate objects. This is like when you, for example, are outside at night and you look at a car coming towards you. If the car is very far, you will see that the headlights, they look like one, not like two, even though you know there are two. As the car approaches you, you will start seeing two headlights. That's because of your resolution that you have with your eyes. Devices like telescopes or detectors, they also have different resolutions. Now, depending on the type of detector, the resolution may be way better than your eyes. So that's the idea behind resolution in diffraction. If light is diffracted through a small circular aperture, like I show you here, you will see that the resolution changes according to what? To the diameter of the aperture and the wavelength of light. So it depends on the wavelength. So the location of the first dark fringe determines the size of the central spot. So that equation that you see there gives you the location. There is no more M, there's no more W, that's the equation. Now, that equation can also be used to find the resolution of a detector. So we're going to be using that when we talk about resolution, for example, in cases like this. All right. So that's another equation that you guys are going to need to understand and study diffraction of light. All right. All right, guys. So the only thing that I'm going to show you before we are finishing is the whole idea behind diffracting gratings and why we use them for acoustic optics, how we can use them to eliminate parts of the signal, change the frequency, and also to use them in spectrometers. All right. Basically, the idea behind diffracting grating is to break light into its components by having several lines per centimeter or millimeter in a rectangular piece of plastic. So at the end of the day, that's what it is. Very expensive, but it's a very important device. Those devices look like this, by the way. There. So these devices that we use them in labs, they come with certain lines per millimeter or centimeter. They allow you to do what you're seeing there. They allow you to basically break light into the rainbow colors. And we can use them in different setups, like this one, which is basically this here, to look at the spectrum of light at different angles. All right, so that's an application of diffraction there. All right. So not many equations on this chapter, but a few new concepts. Tomorrow, after lab, guys, we're going to be doing a review of this and problems on interference and diffraction. Since we're probably going to finish with this in 45 minutes or half an hour, I will have time to go over some problems of the previous chapter on optics. I will probably do some refractions, mirror problems tomorrow. So that means on Wednesday, we can do some lenses and some of what we did before, like magnification, magnifying glasses and such. Any questions before we are finishing today, guys? Okay, don't go because I'm gonna double check the attendance. Okay. All right, so as I said, tomorrow night, all the assignments, all the web assignments will be reopened, so you can start studying for tomorrow. Make sure that if you didn't submit, at least submit them, even though there is a penalty, it's better than having a 0. And remember, assignments can help you increase your grade and also to study for both the quiz and the exam. All right, that's it.
Thank you. Have a nice day, Professor.
Have a good evening.